I want to just go through. All right, here is pros and cons. Con is that this page is not in the test that's on Tuesday, but the pro is it's the same equation. So we're still going to be playing with the same equation. We're now looking at wave harmonics in pipes, which is assigned to week 4 of the topic. Okay. The only difference here is, instead of looking at variations in the string, which is a transverse, we're now looking at sound pressure waves, which are longitudinal. But we can still look at how the pressure is changing and how the particle displacement is changing. Okay? So, harmonics in tubes, areas of repeating interference, instead of superposition of a wave on a string, it's a superposition of the pressure waves that are travelling in a pipe. Okay? Now, I'm just going to read this. As the waves in a pipe travel, they're continually reflecting off the inside walls of the pipe, so we can pretty much treat the pressure wave as a nice plane wave travelling at a constant speed through the pipe. And if it's in this classroom right now, it's going to be about 342 metres per second. Okay? So remember, with our strings, they can vary from 10 metres per second up to the guitar string example from yesterday. The pulse was travelling like 700 metres per second. In air, it's the speed of sound in air. Okay? Now, you might have to determine it, or you will be told what it is. You will be given V, or you'll be asked to find for it. Now, if we have a compression wave travelling through the pipe, once it reaches the end, it's no longer confined, and it rapidly expands out into the universe. What it does is it leaves behind an area of low pressure. That low pressure then gets sucked back into the pipe, and so when you have a compression wave travelling to one end, it gets reflected as a low pressure. And so that's the whole idea, that it's returning or reflecting out of phase by half a wavelength. Now that is exactly the same as the pulse on a string. We said that a crest will be reflected as a trough. Now, let's have a look at the UNSW example of this. Here is, here we go. Oh, thank you, yep. Core i7, bloody 16 gig of RAM, and it can't just zoom out. Frickin' page. Okay, here we go. This is an open-ended tube, open at both ends. Please watch the animation. Compression, boom, gets reflected as rarefaction. Zoom, gets reflected as compression. All right, so every time it reflects off the end of the tube, it returns back into the tube, shifted by half a wavelength. Okay? And so now, that's obviously just one. If I was to have a frequency of sending pressure waves, there will be regions where they're working together and you would get large pressure, and there would be regions where they're working against each other where you would get zero pressure. So instead of a particle node, which is, on your string, you're going to get pressure nodes. Now, pressure nodes are different to particle displacement, but we're going to look at that in a little bit more detail. There is also a video I want you to watch, and let's see if we get flagged on YouTube for copyright. Here we go. Fingers crossed.
That we can excite in different ways. Let's picture the reflection of a pressure pulse. At a closed end, the air can't move, so the compression pulse can only move back along the pipe. So the pressure wave is reflected with a phase change of 0.
By the way,
at a closed end,
we don't normally have two ends closed. You can't really make any sound with a tube that's closed at both ends. You've got to have an open end to create a disturbance, okay? So we're not ever going to look at two closed ends. It's going to be open at both ends or closed at one, okay? But I want you to look at the open pipe.
Displacement must be 0, so the displacement wave has a phase change of pi. At an open end, things are different. Here, the pressure is approximately fixed at atmospheric, so the sound pressure is approximately 0. So the pressure wave is reflected with a phase change of pi. The displacement is free, so the displacement wave has a phase change of 0. Let's look at sine waves in pipes. A flute is approximately cylindrical and open at both ends. Let's keep all the keys closed, so we have a pipe about 60 centimetres long, open to the atmosphere at both ends. So we have...
Turns out I needed to go to potato mode. Fail on my behalf. Maybe tomorrow we'll go to potato mode. But for now, could we please have a look at the last sentence? A standing wave that's formed in an open-ended pipe has maximum air displacement at the open end. Okay? So, you have to be careful. There are two different wave envelopes we can ask to sketch. Let's just sketch the particle displacement. Or I'm going to go a particle envelope. Alright? Now, all you need to remember is that there is always a particle antinode at the open end. So every single tube, you're going to draw antinodes at each end. Now, the first harmonic, or the fundamental, we're going to draw the following. Okay, so this, if you have a look, this is half a wavelength. It's the opposite of this one that we sketched earlier this week at 11 Hertz, please. There we go. No, there it is. Alright, so with the strings, it's the opposite. For a string, we've got a particle node at each end and a particle antinode in the middle. For pipes, it's flipped. We have a particle antinode at each end and we've got a particle node in the middle. You need to appreciate that at an open end, they're free to move. So if you were to watch a particle at the end of a tube, that's where it's going to be moving the most. As the pressure wave travels out and the low pressure wave moves back in, your particle's sort of getting captured in that pressure movement, or that pressure. So it moves the most, okay? So we're just going to sketch something similar to what we did earlier this week. We'll call this the first harmonic. It's exactly the same equation. Lambda n is going to be 2L over n. And if we put that into the wave equation, so that should be lambda 1. Okay. And now we're going to do the second harmonic. But same deal, we're going to have antinodes at the end of each pipe, and then we're going to put an antinode in the middle. And so now this is going to be one wavelength. But again, we don't often sketch wavelengths like that. That's one wavelength. We're just not familiar with seeing it like that. Normally we want to see it like that, which is what the second harmonic of a string would look like. This is the second harmonic of our open pipe. Okay. So let's just fill this in. This would be the first overtone. Lambda 2 is 2L on 2, which is just the length of the tube. Okay. And if you wouldn't mind continuing down, let's just do the next 2, which would be the third harmonic. Again, antinode at each end, And then we're going to have to put antinodes at about 25%, 25, not 50. And then, no, 33%, 66%. Here we go. I'll probably stuff this up. There we go. Definitely stuffed it up. Oh. And then the last one how many antinodes are we going to fit in here? Okay. And so let's just write it all in its entirety. 2L on 4. That should make sense that the wavelength is half the length. So if I split this in half, we've got a wavelength. Okay. Then F4 equals 4V on 2L. So our lambda n is 2L on n. And F of n equals NV on 2L. So exactly the same equation as the strings. Okay. One last useful bit of information that I want to tell you. I'm just redrawing that because I changed its colour. Is that if I went from one antinode to another antinode, this is called the internodal distance. Okay? And that will always be half of a wavelength. Okay? In fact, I could go from node to node. Same deal. It will always be half of a wavelength. That's a useful thing to know because sometimes, and I think I've thrown a question in the exam, if you're changing the length, you're going to hear it go from loud to quiet to loud. And the distance between consecutive loud points is always half a wavelength. In fact, that's what you're going to need to know when you're doing your final prac in week 4. You're measuring the distance between consecutive loud spots. You're measuring the distance between consecutive antinodes. Because have a think, to hear loud noises, you need the particles moving a lot. So you need to have a particle antinode. So you're going to place your ear next to the pipe, and when the particles are moving the most, that's where you're going to hear them. If they're not moving, you're not going to hear them. Yes, Matthew?
Isn't it a full wavelength that's loud? Isn't it half that's quiet?
No, antinode to antinode is going to be half a wavelength, because if I was to go a full wavelength, let's go a full wavelength from here. I've only gone half of a wavelength there. I would have to then go to 2, that would be 2 antinodes. Alright, so that would be 1 to 2. Okay? So twice the internodal distance would be 1 wavelength. 1 internodal distance is going to be half of the wavelength.
Yeah, but isn't that related to half difference?
No. It's just all of the distances, every single antinode that we've drawn has been half of a wavelength apart. Okay? Every node that we've drawn is half of a wavelength. Okay? Now, here's what you need to write down somewhere. There it is. I mean, could you just write this here, please? Particle node equals pressure antinode. And vice versa.
What does that mean?
I'll explain that in just a moment. Write it down. Okay, now, I'm just going to have it on this first harmonic. Here's an antinode for particles. They are moving the most. If they are moving the most, it means that the pressure is working together. The pressure is pushing and pushing the particle out, and then pulling and pulling the particle in. And so if the pressure is working together, we call it a pressure node. Okay? Let's go to the opposite. In the middle here, this is a particle node. What that means is that one pressure wave is trying to push it that way, and one pressure node is trying to push it the other way. All right? And so this poor little particle is getting pushed and pushed equal and opposite amounts in equal and opposite directions, and so it's stationary. And so that is a pressure antinode. The opposite can then also occur half a wavelength later. There might be a rarefaction travelling towards it that's trying to pull it that way, and then there's a rarefaction wave travelling in the opposite direction that's trying to pull it that way. Okay? So this poor little particle in the middle of the pipe is sitting there getting squished and pulled and squished and pulled and squished and pulled at exactly the right time, equal and opposite. And so the poor little particle is just sitting there not moving. Okay? But on this side, you're getting two pressure waves, whoosh, then two rarefaction waves, whoosh, then two pressure waves, whoosh. They're working together, the pressure waves, to produce maximum particle displacement. So when they're working together, we call it a pressure node. When they're working against each other, we call it a pressure antinode. Okay? Now, I'm not going to force you to copy it down, because over the page, let's just have a look. Okay? Now, there are there's lots of tricky parts to these kinds of questions. The first tricky part is you could be asked for either the harmonic or the overtone, so just be careful there. So Mr. Murray will try and test you. He might ask you to sketch the particle displacement envelope of the third overtone. Wow, okay, third overtone, that's the fourth harmonic. Okay, particle displacements. All right, I need antinodes at the end. It gets tricky. Okay, so obviously, I went to both. The first tricky part is you'll either be asked to sketch harmonics or overtones. So you need to know the link between the two. And then the second tricky part is you'll either be asked for particle displacement or pressure variation. Okay? Just on this, I just want to quickly add here, that's where the pressure works together. And as I said before, that might be pressure and pressure. Or let's go compression and compression. They work together, and that's going to equal maximum movement of particle. Okay? i.e. particle antinode. And then obviously in this region, you've got a pressure antinode. That's where they're working against each other. Against. That's not how you spell against. And so that could be a compression trying to push it that way, and a compression trying to push it that way, and that's going to equal 0 movement of your particle. Okay. So, and apparently there's a box. Well, okay, let's put the boxes in. And we'll just highlight that as well. Okay, a panpipe. Easy, yes?
So when it's a pressure antinode, it's a particle node.
Correct.
Please say it's the other way around.
They're the pressure and the particles are opposite.
Ah.
So let's say, take your statement, a pressure node occurs at the end of a pipe. That's where a compression is pushing it out at the same time that a rarefaction is pulling it from the opposite direction. They're working together. It's going to create maximum particle movement. So that pressure node is when the pressure waves work together to cause maximum particle movement. So maximum particle movement is an antinode. Pressure working together is a node. Okay. Here is a panpipe. Easiest example of an open-ended tube. It is a tube that is open at both ends. You blow air across the top, you can make the first harmonic appear. Okay? So, the range of frequencies. Well, the smallest length, have a look at our equation here. Frequency is inversely proportional to the length, so it would make sense that the smallest length would make the highest frequency, and then the longest length would make the lowest frequency. Where are you two going? Okay, good luck. If you're interested, you can watch the last 10 on the YouTube. So, let's just do F maximum is going to be NV on 2L minimum. Let's just throw everything in. We'll go 1 by 346 over 2 lots of 0.15, and that gives a highest frequency of 1150 Hertz.
So I've got 22.15. I've got 1.15.
Thank you. And then let's just do F minimum is going to be NV over 2L maximum. Well, that's easy. That's just 346 over 1. Okay. Let me just tidy that up. Okay, there you go. 2 lots of 0.15 is 0.3, so it's 340 divided by 0.3, kind of like timesing 340 by 3, which is kind of like getting 1,150. For those of you that got the wrong frequencies. That is the range of frequencies. So this guy's going to make a high frequency of 1,000 Hertz down to 346 on the other side of the pipe. How's it go, Hugo? Sure, why not?
Does it matter that it's like curved? Like it's not.
Does what matter that it's...
Yeah, like it's on a slant. Yeah. Like would it?
Google image search panpipe. You'll see some...
No, but like, would it make a difference to the sound if it was like open versus slant?
You mean a tapered end?
Yeah.
I don't know.
Okay.
The end... You got... There is some stuff going on at the end of clarinets where they taper out. That it doesn't affect the frequency, but it affects the sound.
Yeah.
That dude in that video that I attempted to show you, he does something pretty funny. He puts the end of a clarinet on the end of a flute, and it changes the sound of the flute. And then he puts the flute, the reed of the clarinet into the flute, and it changes the sound of the clarinet. So yes, the end of the tube, it doesn't affect the frequency, but it does change the timbre or the sound of the note. Guys, do you have some spare room at the bottom there? Do you have some spare paper at the back page? Back page. Yeah, come on, help me out. Yes, back page. Go to the back page. Guys, I want you to sketch a few wave envelopes. They're either going to be strings or open pipes, because that's where we're up to so far. In the last 5 minutes, I'd like you to sketch the second overtone particle envelope on a string. Okay? So, 3 different things going on. The second, that's the third harmonic. We want the particles. That's great because we don't really worry about pressure on strings. Okay? So, there's the length of our string, and we know that there must be a node at each end of our string. We want the third harmonic, which means we need 3 antinodes in the middle. 1, 2, 3. I reckon we're going to put nodes here. And then I reckon we're going to do that. I reckon I've just given you the bloomin' answer. That is the particle envelope for the second overtone, which is the third harmonic. Okay? Particle envelope means that there is a node at the end. Okay?
So it's pressure variation.
Well, we're not going to worry about pressure variations on strings, but we could. Let's go to the next one. Let's sketch the fourth harmonic pressure envelope of a open tube. Now, you could cheat and go back to page 19. It's got all of the envelopes for the first 5 harmonics. Try and do it yourself. Was it page 19?
Yeah, it was.
Yeah. Try yourself first. Have a go. Pressure envelope. Here's my tube. You can draw the physical dimensions of the tube. Now, all right, we know particle envelopes have an antinode at the end. Pressure must have a node at the end. Okay? If I set up the first harmonic, there would be 1 antinode. The second would be 2. The third would be 3. The fourth, I reckon we need to set up 4 antinodes. Equally spaced. Try that again. Equally spaced. Nope, stuffed it up. Oh, stuffed it up. Go back, come on. Oh, hello, keyboard. I didn't want you there, but... Okay. Boom. All right, let's go one easier. Let's go the first overtone particle displacement of open tube. So again, first overtone, read that as the second H-monic. Particle displacement. Okay, we know at the end of a tube we have antinodes. So sketch them in. Straight away, you draw your tube. I know there's an antinode for particles at each end. I'll give you a hint. We sketched this. It was the second envelope that we sketched on page 18. And if you want to look, you can check with So I reckon the second harmonic, you need to sketch 1 full wavelength in that tube. There's going to be 1 more antinode in the middle. And we're going to sketch that weird wavelength like that. Okay. So that is the first overtone particle displacement envelope of an open-ended tube. Yes?
So for an open tube, a pressure is known at the end, particle is
Yes.
at the end.
So
The
guys,
string is nowhere.
For you lot, for sketching this, I recommend just remember what the particles are doing. And you just know that the particles at an open end of a tube, they are free to move in and out as far as they please. So I would always just remember the particles, and then just go, pressure's the opposite.
Yeah.
Okay? Are we ready to go? Okay. So, guys, remember what I said. You've got three tricky things going on here. Harmonics or overtones, pressure or particle displacement, strings versus tubes. Okay? So that's you got to think about what you're sketching. Okay. See you, gang.